And actually, what I can do, I'll share my screen and I'll try and remember to stop sharing. Hey, Meg. So it's just mentioned to Luke that I have a mistake in my preamble. Surprise, surprise. Sorry, Luke. Everybody's seeing your first attempt here. Okay.
No worries.
There's no balance on it.
So Luke very correctly, given what I'd put up, oh, sorry, I have to share. I have to actually share my screen here.
No, you're not.
Protecting Luke's privacy. So there we go. So I said this line lies on this plane, and what is the dot product of the direction vector of the line and the normal vector of the plane? Or at least that's what I should have said. Now you'll notice that I have 2, 1, 1 as the direction vector here. Well, it turns out that that's not the correct direction vector. The correct direction vector is actually 2, -1, and 1. So you can see in GeoGebra I've had to enter them as parametric equations. And so what we really need to do is the dot product of 2, -1, and 1 with the normal vector to the plane, which is -4, -3, and 5. And yeah, let's just do that, and we'll talk about the result. The earth-shattering result of that dot product. Did you get an answer, RJ? Did you get an answer, Luke?
I got a t equals 0, so I think I screwed up somewhere.
What'd you get, Meg?
Nothing yet.
Oh, if by nothing you mean 0, that's, what did you get, RJ?
0.
0, yeah. So in fact, the fact that that line lies on the plane means that it will be perpendicular to the normal vector. And so when you take the dot product of 2 vectors that are 90 degrees to each other, the answer is going to be 0. Because dot product and cosine are sort of closely related. The cosine of 90 degrees is 0. So when you do the dot product of a line on the plane with the normal to the plane, you're going to get a 0. So this is actually pretty short, so you probably noticed that it's actually a pretty easy lesson, because pretty much you're just putting parametric values for the variables into the equations, and you're seeing if you get a value for t or not. So here we have a problem where we're given a line, position vector 1, 0, 4 plus t times the direction vector -2, 2, 1. And we're given the plane 6x plus 2y plus 3z minus 12 equals 0. The first problem is we need to show that they are not parallel. And that sort of nicely plays off what we just saw as being my mistake when I set up the question. Oops. RJ, any ideas how we might show that those two are not parallel?
Changing the parametric ones, so then, like, multipliers by 20 into the function.
Okay, so RJ's saying, you know what, I can change this into the parametric form from the vector form. I can substitute it into the equation for x, y, and z. And if I get a value for t that makes sense, then those two aren't parallel. Or that, because that would mean that they intersect, right?
Yeah.
Yeah, and that would work. There's actually an easier way. Any ideas how we could do it a little bit easier, show that they're parallel? Meg, any ideas? No?
Could we have something with the slope?
Yeah.
I guess not, because
Because if they're parallel, basically the slope of this would be the same as the slope of the line. And, the slope of the plane. Basically, we can find out, we can take the perpendicular vector to the plane, and we can do the dot product with the direction vector of the line. If that turns out to be 0, then we know that they're parallel. Okay, so if they're parallel, the angle between them is going to be 0, but the angle between the line and the normal is going to be 90. So all we really have to do is take the dot product here, and what do we get? We get negative 12 plus 4, which is negative 8, plus 3. We get negative 5. So the dot product is not 0. So the line and the plane are not perpendicular. So they're not parallel. Okay, so you can do things like that. You can use the normal sometimes. Because it's a little bit tougher, it's a little bit more work to actually get some vectors when we're just given the equation of the plane. So we're going to look at a second problem, and we're going to do this with the exactly the same line and the same plane. So we're going to try and find all the points that are on the line that are exactly 2 units away from the plane. Okay? And if you can imagine, this line is probably intersecting the plane somewhere. So we're going to have 2 places where it's going to be about 2 units away from the plane. Okay. So does anybody remember that distance formula from yesterday? So the distance from, so if we're going from x, y, and z
Oh,
to a plane,
AX
ax,
plus UY plus CZ minus AX0 minus EY0
Plus T.
plus D. Yeah, so you're actually thinking about how we derive that, RJ, but it's actually plus D. So it's the result of the projection. And it's all over a squared plus b squared plus c squared. That's equal to the distance. Okay. So we're going to get 2 points, but we've got x, y, and z here, so this is going to be difficult to solve because we've got 3 variables. It would be better if we could get up these all in terms of 1 variable. Well, really, we know what a, b, c, and d are, right? Because a, b, c, and d are 6, 2, 3, and -2. But x, y, and z, those are 3 variables. And it would be nice if we could express them in terms of a single variable or parameter. So, go ahead.
T.
Yes. So we're going to express x, y, and z in terms of t. So we're just going to express them parametrically from our line here. And then we're going to substitute a 2 in for d. And then we'll solve for t that way. Okay? So this is going to become 6 times 1 minus 2t plus 2 times 2t. Uh-oh, I'm in trouble. Plus 4 plus 4t, or sorry, plus 3 times 4 plus t. Plus b, which is minus 12. Okay. Sorry, everybody. If that looks like a 16, those are absolute value brackets there. Okay. So I just got my a, b, c, and d from this plane here. Now I'm going to go square root of a squared, so 36 plus 4 plus 9. And I know that we want that to be 2 away from everything. Okay, please inspect that for any errors. Minus 2t, 2t, 4 plus 2, minus 12. Okay. So going way up here. That's minus 12t plus 4t plus 12 plus 3, 2 plus 12. All over. Square root of 49.
That almost seems like a perfect square.
That's amazing. Who would have ever guessed? That's nice. I like it when things work out like that. Almost on purpose. Okay, so now we have to do the awkward.
Well, the other cancel, so that makes it a lot easier.
12s cancel, good.
That leaves you with a 6, and then 4, 3, and then 12. That's negative 5t.
6 minus 5t. Absolute value equals 7. is equal to, why don't I just,
Make it 4 equal.
I'm just gonna say it's equal to 14. We're big people around here.
Big numbers don't scare us.
Big numbers don't bother us. Combining steps doesn't bother us. Okay. The absolute value of 6 minus 5t is equal to 14. So we have to take into account the fact that this could be negative
Or positive.
or positive. That's right. So 6 minus 5t could be equal to 14, or 6 minus 5t could be equal to negative 14. Now we just have to solve for t. So just like we'd expect, we're getting two values for t. T is equal to, what is this? Or t is equal to, oh, and this comes out to a lovely 4. One of them is not even a fraction. That's pretty nice. Okay. So we aren't quite done, but I don't think we have to. I don't think we have to go too crazy. If we were going to finish off this B part of the question, what would we need to do now that we have our t values? So RJ just said solve for x, y, and z. In other words, we're going to plug t into the two values of t into this equation, and we're going to figure out what our x, y, and z are. Yes, that would be exactly it. Okay, and that will give us our 2 points. Okay, the last question I'm going to ask today, so it's a pretty easy lesson, and the preamble covers most of it. I always kind of liked imagining these planes, trying to imagine what they look like in 3 space. So we'll give that a shot. So I used to always look at the scalar equation of the plane. Basically, all I did was I found what the x, the y, and the z intersections were, and then you could kind of get a picture of. You can get a picture of what the plane looked like in 3 space, what it looked like in that little boxy thing that we see in GeoGebra. So let's take a look at the x, y, z intercepts of the plane. And this is pretty easy to do. So when that plane is intersecting the x-axis, what's the value of y and z? This is easier than you're thinking.
0.
Exactly, yeah. Y is going to be 0, Z is going to be 0, so all we really have to do to find the x-intercept is just substitute a 0 in for y and z. Things get really easy. So x is 2, That's my x-intercept. So the y-intercept, and actually, you can almost just basically look at it. 2y minus 12 equals 0, so y is 6. Z-intercept, three z minus 12 is equal to 0, so z is equal to 4. I'm just going to bring up the GeoGebra and we'll take a look at it. See if we got it right. So if you get a chance, actually download GeoGebra because it's a free program. And I actually met the creator. Believe it or not, I was at a conference. I was at a GeoGebra conference in North Bay, of all places. And Marcus Horenwerder. Oh, there's absolutely nothing wrong with North Bay, actually. It was a lovely place. And anyway, he was the creator of GeoGebra, and we actually kind of hung out together a little bit. And the creator of Geometer Sketchpad was also at the same conference. And so they had kind of two competing products. One guy's was free, and the other was not. The guy who invented Geometer Sketchpad, he was from like California. He was pretty urban. He was pretty fancy. And the guy from Austria, he was a little more, seemed a little more homespun. Anyway. Okay, so there we go. As you can see, we've got, I don't know if you can see it. Does that show up okay for you guys? Yeah. Okay, you can actually see there, you can see the planes intersecting the x-axis at 2, just the way we'd kind of calculated. You can see that it's intersecting the z-axis up here at 4, and you can see that it's intersecting the y-axis at 6, just the way we predicted with looking at the intersections. So you can get a kind of an idea what the plane actually looks like just by doing the intersections. Okay. So that's about it. I just have sort of a few questions in the exercises picked out somewhere. I actually have them written down. There we go. Huh. Okay, so for exercises, we'll just do 1 to 5. So that's in the CEMC lesson. So those are all, they're all roughly the same. I think the biggest trick is going to be converting everything, figuring out how to convert it into parametric form. Okay. So that's it. We're on target. We're almost done. So this was intersection of a line and a plane. Tomorrow we're going to do the intersection of 2 planes together. So when 2 planes intersect, what does the intersection look like? What do you get when 2 planes intersect? RJ's actually doing the... Oh, Meg's doing it, yeah. Yeah, what's the result? Is it a point?
Maybe so. Maybe a line.
It's a line, that's right. So when two planes intersect, they intersect in a line.
When they have a direct-
However, there's an exception.
If they just touch down on it, only at the corner.
Well, planes go on
Oh, yeah.
infinitely, yeah, unless we restrict them. There's only one other exception that would be
Parallel.
if the lines are parallel, they'll never meet. So that's the way a solution could go, okay? Otherwise, we have like exactly the same two planes, but they would be defined in some other way. Okay, good. So we're good for tomorrow. Can you come tomorrow, Luke?
Yeah.
All right, great. And RJ is doing the intersecting galloping lines. Okay. All right. We'll see you tomorrow.
Anyways,